Hello everyone, welcome to the course on tribology, that is 17ME742 of mechanical engineering. Today we will see the module 4 of our course tribology. The module 4 is hydrostatic bearings. So we have seen in module 3 hydrodynamic bearings and hydrodynamic journal bearings. So now first before entering into the module 4, that is hydrostatic bearings, let us understand the basic difference between hydrodynamic bearings and hydrostatic bearings. Hydrodynamic bearings, hope you might be remembering the explanation that we have given for hydrodynamic bearings. The bearings, hydrodynamic or hydrostatic, generally they are non-contact bearings which are going to exert the pressure or they are going to take the load by only because of the oil that is present between the stationary member and the rotating member. In the oil that is being present between the stationary member and the rotating member has to be pressurized, or it has to exert some pressure so that it is capable of taking the load that is acting on the bearing, acting on the journal. So how this fluid or the lubricating oil is going to take the load? So this lubricating oil will take the load by two principles. The first principle is by hydrodynamic nature. The hydrodynamic nature is at the first instant the normal or the unpressurized or the regular oil is fed through the pump into the bearing chamber and the machine is switched on. As the machine is switched on, at rest, at the initial, the journal and the bearing are in contact with each other, and as the machine starts progressing towards, as the machine starts running slowly and it picks up the speed, the rotation of the shaft or rotation of the journal will make the fluid that is between the journal as well as the bearing surface to squeeze, and this squeezing will make the fluid to induce the pressure, and this rotation of the shaft will induce the pressure between the bearing chamber as well as the shaft or the journal. This mechanism or this principle of generating or exerting the pressure between the bearing chamber and the shaft by virtue of the rotation of the shaft or virtue of rotation of the journal will be called as hydrodynamic. Dynamic because of the motion. Because of the motion, the pressure is exerted or pressure is induced by in the bearing chamber by the lubricating oil. By this method or by this principle, the lubricating oil is capable of taking the load that is acting on the shaft, or the entire shaft load is taken up by this lubricating oil or this fluid film that is between the bearing chamber as well as the journal. So now this hydrodynamic case is possible when the load is relatively low and the relative velocity between the shaft and the stationary member, that is the bearing bearing surface, is too high. If the load acting on the bearing surface is high, if the load acting on the bearing surface is high and the rotation relative velocity between the shaft as well as the bearing surface is too low, then the speed is low, that is it is at the initial stage, at the rest, as we seen in the hydrodynamic case. If the relative velocity between the stationary surface and the moving rotating surface is too low, then there will be a metal to metal contact in the bearing chamber. This metal to metal contact will make the surface of the shaft or make the surface of the both shaft as well as the bearing chamber to wear off, or it is going to lose some amount of material. So how can we avoid this scenario? How can we avoid this scenario where the load acting on the journal is too high and the relative velocity between the two member is very low? If this scenario has to be eliminated, then an lubricating oil should be fed so that it will have a pressure which is capable of taking the load that is acting on the journal or the entire load that is coming on the bearing surface, So this fluid which has to be supplied between this chamber, between the bearing surface and the shaft needs to be pressurized, whereas in hydrodynamic the fluid gets pressurized by itself due to the rotation of the shaft. But in that case, where in hydrodynamic case, the load is low and the relative velocity between the two members is very high. When the speed is very high, the squeezing or the pressurizing the fluid will be very high. But in this scenario, where the load is high and the speed is slow, the member is not able to generate that amount of pressure. So the fluid will be at the normal state, or it will be in a stationary, or it will be in the atmospheric pressure state. So how to make this fluid to capable of taking the load that is acting on it? So this can be done by introducing a lubricating oil capable of taking the load that is exerted by the shaft or the journal by making this fluid pressurized from some external source, like compressors or so on. So this externally pressurized fluid is fed through the chamber, which is going to occupy the space between the journal as well as the bearing surface, will be capable of taking the load that is acting on the shaft or the bent bearing. So this externally pressurized fluid will avoid the metal to metal contact even at the low speeds. So by this we can understand this principle, where an externally pressurized fluid is fed into the bearing chamber, which is capable of taking the load acting on the shaft or on the bearing, which is going to avoid the metal to metal contact, can happen only when the load carrying capacity is high or the load acting on the bearing is high and the speed is relatively low, or the relative velocity between the two surfaces is low. So this is where we can use the hydrostatic bearing. So this method of introducing an externally pressurized fluid to take up the load is called as an externally pressurized bearings. So this type of bearings are called as externally pressurized bearings, or they are also known as hydrostatic bearing. Even we call it as a footstep bearing. Now let us see an hydrostatic step bearing. In hydrostatic step bearing, as we have seen in the figure, we have a rotating member which is called as a shaft and a stationary member which is called as a bearing, and the fluid is supplied to this bearing chamber with a centrally cut channel. Through a centrally cut channel, this is a channel through which the pressurized lubricant or the pressurized fluid is going to be fed inside the bearing chamber. So you can observe there is a recess or there is a pocket that is made on the shaft, on the underneath of the shaft, where it is going to come in contact with the bearing surface, This recess or this pocket may be cut either on the shaft or even on the stationary member, or in certain cases it might be cut on both the members. It can be cut on both the members, that is, it might be cut on the shaft or also on the bearing surface. So the lubricating oil is going to be present on this pocket, which is present on the shaft or on the bearing surface. So as the speed increases, this lubricating oil which is present on the pocket, it is going to spread, or it is going to exert the pressure radially along the surface of the shaft. It is going to spread radially along the surface of the shaft. You can observe there is a load acting on the shaft. This load acting on the shaft is taken up by the pressurized fluid that is present between the shaft as well as the bearing surface. The clearance between the bearing surface and the shaft is taken out as H, that is the clearance between the bearing surface and the shaft or the journal. So this is how the step bearing is going to work. So we will have a load acting on the shaft, and we have a bearing surface which has got a centrally cut pocket or a channel through which a pressurized fluid or a pressurized lubricant is going to be supplied, and this pressurized lubricant is going to occupy the space that is provided on the shaft or on the bearing surface, which is nothing but a pocket. This pocket is going to carry the entire pressurized lubricating oil. As the load is going to be applied, this pressurized lubricating oil will spread radially along the surface, and this will take up the load that is acting on the shaft. So this is how an hydrostatic step bearing is going to function, or this is how the hydrostatic step bearing is going to work. Or this is the working, we can also call working principle of an hydrostatic bearing. So here, as we have seen, the load is very important parameter, and another thing is the fluid that is going to be supplied. That means that why I have stressed on the load and the lubricating oil that will be supplied is, these two are the very important parameters, because as the load increases, I should be knowing what amount of lubricating oil has to be supplied at what pressure, or if I am going to supply at certain pressure and at certain volume, I should be aware what is the load that is acting on the shaft. That means to say, we should establish a relation for load carrying capacity of the hydrostatic bearing and the flow parameter, that is Q, the flow parameter on the hydrostatic bearing. So these two are the very important derivations that is going to come in hydrostatic bearings. I will just rewind or just brush up few things, that is hydrodynamic and hydrostatic. We have two types of bearing, hydrodynamic and hydrostatic, in non-contact under hydro. Hydrodynamic means the pressure between the bearing chamber and the shaft or the journal is produced due to the rotation of the shaft. During the rotation of the shaft, the pressure is applied, the fluid gets squeezed, and because of the squeezing effect, the member is going to induce a shear stress, and this shear stress will produce the required amount of pressure which is capable of taking the load at this acting on the bearing. In hydrostatic, the load is high whereas the speed is low. Due to this low speed, there will be a metal to metal contact between the two surfaces. If this metal to metal contact between the two surfaces is not avoided, then our bearing will not be that so effective. So in order to make this bearing more effective in functioning, we will do some modifications to our bearing. That is, we will supply, instead of a unpressurized fluid, we will supply a pressurized fluid between the bearing chamber and the journal. What will this very pressurized fluid do? This pressurized fluid will take up the load that is acting on the bearing, and it will avoid the metal to metal contact, thereby the effectiveness of using this hydrostatic bearing will be enhanced. So this is how this is the difference between dynamic as well as the static. Okay, after knowing the difference between hydrodynamic and hydrostatic bearings and understanding the principle of hydrostatic step bearing, let us move forward to derive an expression for flow rate in an flow rate through hydrostatic bearings. Flow rate through hydrostatic bearings. Consider an hydrostatic step bearing which is as shown in the figure, So W is the axial load or the thrust load acting on the shaft, D1 diameter of the recess or the pocket, and R1 corresponds to the radius. D1 is the diameter and R1 is the radius. D2 diameter of the shaft, and R2 is corresponding radius of the shaft. P0 is the oil supply pressure. It is the pressure through which the oil is fed into the bearing chamber. So remember, it is an hydrostatic bearing. The P naught value will be the pressure, externally pressurized fluid is going to be fed. So P naught will be certain pressure, certain value of pressure by which the fluid is fed, and that pressure will be maintained inside the bearing chamber, which takes up the load, entire load acting on the bearing. PA, P suffix A, the atmospheric pressure, or we can generally call it might be 0 or the atmospheric pressure. H, fluid film thickness. It is very, very important. What is the film thickness that should be maintained between the chamber as well as the shaft, because this will give you the load carrying capacity. This parameter will influence the load carrying capacity of a bearing very much. Q, the flow rate. The value, the derivation is entirely based on determining the expression of this parameter, that is Q, the flow rate of the fluid that is going to be fed inside the bearing chamber. Neta, neta, viscosity of the oil. Again, viscosity also is a very important parameter, because as the temperature and other things vary, temperature and pressure vary, the viscosity is going to vary. This we have discussed, what is the influence of pressure and temperature on the viscosity in the first module itself. So this viscosity again is a very important parameter to come up with an expression for flow rate of a flow rate through the hydrostatic bearing. So let us start our derivation. I hope you have understand the diagram. W is the load acting on the shaft, D1 and D2 is the diameters of the recess and the shaft respectively, and P naught is the pressure, that is oil pressure that is supplied, PA is the atmospheric pressure, and H is the fluid film thickness, Q the flow rate where we are interested in, and neta is the viscosity of the oil that is being fed inside the bearing chamber. So to start with, consider an elemental ring of thickness dr. The hatched portion what we are seeing in the diagram is the elemental ring. We are considering a small element, small portion of that elemental ring, and that is having a thickness of dr, a small thickness of dr, which is at a radius r. So remember, r1 is the radius of the recess or the entire pocket, r2 is the diameter of the shaft, and r is the radius at which the fluid elemental ring is considered, and it is as shown in the figure. So remember, in the second module or in the third module of course, we have derived an expression for flow between the parallel plates. Flow between the parallel plates, or using the Huygens-Poiseuille's law, that is flow between the parallel plates. In that flow between parallel plates, we have established a relation for oil flow rate. We are taking that particular expression. The oil flow rate is given by Q equals BH cube divided by 12 neta into dP by dx, or we can call this as a pressure gradient. You can observe neta, viscosity, and the film thickness. As I was earlier saying, film thickness and viscosity are very important parameter for this Q. What is Q? It is the flow rate. B, it is the length of the parallel plate. Here we derived this expression for flow between the parallel plates, which are flat in nature. But in our present scenario, we are establishing a relation for flow rate for a circular member, that is a shaft as well as the bearing. So how to modify this? So considering an oil flow through an elemental ring is considered at a radius r, and the thickness of the elemental ring is dr. So the dx is replaced by dr, dx becomes dr, and b becomes 2 pi r. What is 2 pi r? It is circumference of the elemental ring. Thereby the above equation, which was derived for two parallel plates, gets modified as 2 pi r. We have just substituted in the place of dx as dr, and in the place of b as 2 pi r. So Q becomes 2 pi r h cube divided by 12 neta dP by dr. So here in earlier, the pressure gradient is along the length of the plate, whereas here the pressure gradient is along the radius of the pocket. So since it is at the radius of the pocket, so we have a negative sign. Why we have a negative sign? Because the negative sign will indicate the pressure is going to decrease as the radius is going to increase. That is, from the center to the periphery, the pressure is going to vary, and how it is going to vary? It is going to come down. That means to say, at the center the pressure is high, at the periphery the pressure will be very low, or vice versa. That is why we have got a negative sign, because the pressure will be a negative slope. It is going to fall down. At the center it will be maximum, at the periphery it will be minimum or negligible. So, we have a negative sign, we have used a negative sign for that. Okay, let us continue. So, we have established an equation for Q. On simplification, Q equals 2 by 12, we had 2 by 12. So, on cancellation we get minus pi r h cube divided by 6 neta dp by dr. Now, we will rearrange the equation to get an expression for P, that is dp I have just cross multiplied. This 6 neta will go to the numerator, minus 6 neta into q divided by pi r h cube into dr. So, this is the pressure on the elemental ring which is considered at a distance r, considered at a distance r. To get the total pressure, acting on the entire pocket, let us integrate the above equation. So, on integration we get P equals minus 6 neta q divided by pi h cube ln r natural logarithm r plus c. So, this c is an integration constant. So, let us call this equation as equation number 1. To get this integration constant c, so we need to apply the boundary conditions. What are the boundary conditions? The boundary conditions are simple. We have already discussed that. That is, at center the pressure is high, and at the periphery the pressure is 0, or the atmospheric pressure. So, at the center the pressure is the pressure at which the oil is supplied, that is at R1 P is equal to P naught, at R2 P is equal to Pa, or the atmospheric pressure. So, by applying boundary condition 2 in our equation number 1, we get the constant, that is integration constant C. So, let us call that as equation number 2. So, this integration constant is applied to equation number 1. So, we get an equation for P, we have an equation for P. So, when we apply for equation number 1, we get minus 6 neta q divided by pi h cube ln r plus 6 neta q divided by pi h cube ln r2. So, on simplification, we get an expression for P as 6 neta q divided by pi h cube ln of r2 by r1. So, by applying again the boundary condition 1, which says at r1 P is equal to P naught, and simplifying we get an expression for q, that is P naught pi h cube divided by 6 neta ln r2 by r1, or we can call that as d2 by d1, which is our equation in page number 23.67, equation number 23.144. So, this is the derivation for flow rate through hydrostatic step bearing.